he's going to be talking not about the thing I mentioned earlier, but about a new paper that published just very recently.
Bueno, okay. Oh, well, thanks for having me here. And today I will talk about, as Joel said, a paper that we published the last year in collaboration with Joel, of course, and Sandy Faber in UC-HiPACC and Vladimir Avila at UNAM. So the motivation for this paper actually started when I was a PhD student. And one of the questions that I always asked myself was, if we observe these two quantities, which we have the stellar mass function, which is the number of galaxies per comoving volume, and the star formation rate and evolution of these two observables, are these two observables consistent between each other? And how can I show that? So I'm not the first one to ask this question, but several people have tried to answer that question. No? Actually, if we want to build models for galaxy formation, and somehow we are trying to answer that question. So, but I wanted to do in some empirical spirit. So I've seen some papers where they do something really simple and very very intuitive way. So basically, if you have the stellar mass function, which is shown here, and you have the star formation rate at different epochs, and then you feed your galaxies with the star formation rate laws, then you can evolve your stellar mass function, assuming that the galaxies are growing only for star formation rates. But this is more complicated because galaxies also merge. So how you can understand that in this very simple picture? And the thing is that, how do you know, also, there are also puzzle questions about that. And how do you know that the galaxy is only moving around the average relations, which is most of the time that the people is using in this kind of schemes. So what I thought is that we, under these considerations, under this picture, we don't have the right clocks, as Sandy said the other day, that we don't have the right clocks in order to understand how the galaxies move or how the galaxies evolve around this correlation between the star formation rate and the stellar mass functions. Okay? So a simple way that I thought that it will be interesting is to use the dark matter halos as the clocks for the evolution of the galaxies. Like, for example, if we have a way to connect the galaxies with the dark matter halos, then we can use the growth of the dark matter halos as a clock to see how the galaxies are evolving in terms of stellar mass, for example. And this is what we did. So basically, this is the empirical modeling that Peter Beruzzi and Ben Monster have been pushing in the last years, using everything that we know from this for our theory of structure formation, feed it with some observables, that to project in order to constrain the galaxy halo connection, and then to project all the halo properties into observables. So this is what we did in our paper. So basically, we use the abundance matching technique, which for the people that is not very familiar with that technique. So basically, you use the galaxy stellar mass function, the cumulative galaxy stellar mass function. You choose some stellar mass, then you compare with the halo mass function, with the cumulative halo mass function, find which halo holds for the same number density, and then look in the plane into galaxy stellar and to the stellar to halo mass relation to your galaxy. Then you do you repeat the same process for all the halo masses, and then you have this particular relation where you have that for low mass halos, this ratio is low, then peaks around Milky Way side, and then it decreases with halo mass. Okay, and if you have that information as a function of time, so basically in this, I will show this for a very simple model in which imagine that this stellar to halo mass relation is independent of time. So then if you evolve this model, what you will do is that by using the growth of the dark matter halos, you will increase in mass in this direction, but at the same time, using this relation, you will increase in stellar mass, and thus you can infer star formation rate, for example. But the situation is a bit more complex. So one of the things is that which are the right stellar mass functions and which are the right observational star formation rates in order to constrain all these correlation between galaxies and dark matter halos. So what we decided is to use a large sample of observables, which are tabulated here, all the stellar mass functions that we use, all the corrections that we need to apply in order to be consistent between these observables, and all the star formation rates that we use, and also the corrections that we apply in order to have a consistent observables. Okay, so so then we can do what I said, just the growth of the dark matter halos, feed with the stellar to halo mass relation, obtain the growth of the galaxies, and then project these quantities into the galaxy stellar mass function, the star formation rate, and the cosmic star formation rate. Here, the observables are shown with the circles, and our models are shown with the solid lines, also here and here. So you see that there is a good agreement between what we found with the observables. They were constrained by the observables. So for the people who loves the mathematics, here are shown some equations on how to derive this. So here are the results. So these are our stellar to halo mass relations from 0 to 10. So you see that we are plotting here the stellar to halo mass relation. So you see that for low mass halos, there is not so much evolution, while for Milky Way size halos, there is a bit of evolution. You can see better here, where we are plotting the ratio of the stellar to halo mass relation as a function of time. You see here the evolution that I was saying. And we had a discussion about that on Monday. And one of the things that I could say is that if you can imagine a model where there is not evolution on the stellar to halo mass relation, what would be the implications, for example, for the star formation rates? Do the star formation rates are doing this, or the stellar mass functions? So what I could tell you, if you have a model where there is no evolution in the stellar to halo mass relation, you will see this, that the solid black line is our model, the model fitted by the observations, while the red solid lines is the model with no evolution. You see that there is a disagreement between star formation rates and of the model of evolution without evolution. So then, when you ask the question, is there an evolution of the stellar to halo mass relation? I would say that you don't only think in terms of the stellar mass function. Of the evolution of the stellar mass function is not enough. You need to think also if you are reproducing the star formation rates. Here are some comparisons with other works, with the classic work of Peter Beruzzi and Ben Monster, also with the models of Young. And more or less, even if we are using very different observables within the scatter, we are very consistent with each other. Here are some results of how is the growth of our galaxies. This is a 3D panel where we are showing the growth of the stellar mass, halo mass. This is redshift. And here you can see color-coded the star formation rates of our galaxies. And this is the projection of this panel. So what I would like to show is that, in the next slide, let's focus on these two panels. But first, because we can always project observables in terms of the evolution of our galaxies, one of the interesting things that we did is to see what is how do the transition mass of quenching, meaning that the mass where the galaxy stellar mass function of quench and star forming galaxies cross, how this mass translate into our tracks of the stellar mass, of the halo mass and the stellar mass growth when we color code with the star formation rates. And I think this will make happy to Abishai, because in his model he shows that around 10 to the 12 the virial shocks become important at low redshifts for quenching the galaxies, but also cold streams could help to maintain the star formation rate on massive galaxies and thus massive halos. And you can see that this mass transition that I was saying, is around here, very consistent with this model. Also, we are showing here the same thing, but for stellar masses. And we also thought that it was interesting to see how was the ratio between the specific star formation rate and the specific mass accretion rate. So basically, this is we are seeing the competition between the growth of the halo, time scales for the growth of the dark matter halo and the growth of the galaxies. If this ratio is equals to 1, it means that the galaxy and the halo is co-evolving. If this is larger than 1, it means that the galaxy is growing much faster than the dark matter halo. And if this is lower than 1, it means that the halo is growing much faster than the galaxy. And we see that more or less the transition between the Virial shocks and the cold streams, the dark matter, we enter into a region where the galaxy is growing much faster than the halo, and then when the dark matter halo is growing much faster than the galaxy. Mm-hmm. But we also thought, well, if we have all these tracks and we have observations that are as a function of the stellar mass, then we can use these tracks of evolution to project into another observables. And one of the things that we thought that it was interesting is to see how is the structural evolution of the galaxies. And this is motivated by all these results of, for example, Sandro Takela, Barro, and to see how the sigma 1 evolves with time, okay? So, and the way that we did is to look into correlations between effective radius and stellar mass. So this is what we infer in our models. And the idea is to project this, is to assign this effective radius into our dark matter halos and the tracks of the dark matter halos, tracks of stellar mass. But because in our model, we are inferring all the average tracks, the idea was to, we cannot just separate correlations between blue and red galaxies. We are plotting here the effective radius as a function of the stellar mass for different redshifts. So then we inferred the median correlation between these two correlations of blue and red galaxies, and then use this correlation in order to infer how is the evolution of the surface density as a function of redshift for the tracks of our halos, which is the thing that we are plotting here. So I'm plotting here the surface brightness as a function of radius for different redshifts for dark matter halo progenitors of this mass at redshift 0. One of the assumptions is that we are saying that all the star-forming galaxies are this with CERSIC index equals to 1, and all the quench galaxies are spheroids with CERSIC index equals to 4. And the idea to think about what we are doing is like if you are stacking images of all the galaxies at a given redshift and a given stellar mass, okay? Which is something that I'm trying to show here. So then we can evolve our galaxies in terms also of surface density or sizes. In this case, what I'm showing is the evolution of our dark matter halos, and color code with the sigma 1 that people has been discussing during this meeting, which is the mass inside of 1 kiloparsec divided by 1 kiloparsec to the square. So one of the interesting things is that in the regime where we see that, so one of the interesting things is that you see that more or less sigma 1 is parallel to the tracks of halo mass, right? It goes like this. But then you see that there is an increase of sigma 1 for the most massive halos where you expect that there are the most quench galaxies. This is a more simple figure where we are showing the tracks. This is redshift, this is sigma 1. We are showing the tracks for the different dark matter halo progenitors. The black one, which is the one of the most massive halo, of the one of 10 to the 15, you see that the halo, that sigma 1 is increasing, and when we approach to the sun, to the transition mass of quenching, you see that there is an increase of sigma 1, and then once the galaxy is quenched, the sigma 1 keeps constant, basically very consistent with the situation that Abishai has been discussing about the theory of the sigma 1. And also you see that when you compare this to the star formation history of the same galaxies, you see that there is a peak corresponding to the increase of sigma 1 the galaxy. And we also we can also infer to compare how the sizes of the galaxies compared to the minor and major rates. So what we are showing here is the historical evolution of the size, of the increase of size of galaxies for these progenitors. And as Sandy showed, in this figure, when you project the effective radius into this figure, you see that basically galaxies evolve like in parallel trajectories. And one of the main conclusions that we got from when comparing these two figures is that basically this increase in effective radius could be due to minor majors. And yeah, so and also one of the other things that I would like to discuss in this talk is that we've been discussing a lot about the assumptions, and in this meeting we've been discussing about a lot about abundance matching and how to interpret abundance matching. And one of the things that I would like to draw your attention is that yes, abundance matching is a really simple, it's a powerful way to project all observables into all the theory into observables, but keep in mind that abundance matching, so for example, abundance matching always assumes that the stellar to halo mass relation of central galaxies and satellite galaxies are identical, which might be wrong. So in a previous papers, in Rodriguez-Puebla 2012, A and B, we showed that this cannot be the scenario. That if you want to be consistent between galaxy groups, the 2-point correlation function, you need to relax this assumption. And the assumption is that if the stellar to halo mass relation of centrals and satellites are different, you can reproduce all these observables at the same time. In the sense that what we are showing here, that the stellar mass of central galaxies lies below of the one of satellite galaxies. And the average correlation is basically what we obtain using abundance matching. And you can understand this in very simple terms. So when you use the subhalo mass, either MPIC or MAC, when the halo center into when the halo becomes a subhalo, basically you're freezing this axis. But it doesn't mean that the galaxy will freeze in the stellar mass, but they need to still growing in stellar mass. So then this will create this segregation into the stellar to halo mass relation. And also, there is another thing that we should start to think about abundance matching, whether the stellar to halo mass relations of red and blue galaxies are the same. This might be also not the case. So in Rodriguez-Puebla 2015, we showed that for a given stellar mass, blue galaxies live in less massive halos than red galaxies. If you want to be consistent again with galaxy groups and the 2-point correlation function. So you can think in terms of that the stellar to halo mass relation should be modal, and the third parameter should be the color. And also, it would be important to understand whether the galaxy-halo connection or abundance matching is consistent with environment, which one of our students, Radu Dragomir, just preparing this paper, he's doing a photometric catalog based on abundance matching and testing whether the galaxy-halo connection depends on the environment or not. So here, Radu make a mock catalog, a mock photometric catalog with all the bands in the SLOAN, and he measured the observed luminosity functions in all the bands and used this for abundance matching, and showed that while very simple, that is that the luminosity to halo mass relation could, as a good approximation, could be think as independent of the environment. So here we are showing the luminosity functions. The circles are the SLOAN, while the results from the Bolshoi simulation are shown with the shaded areas. And also we showed the same thing for the stellar mass. And well, I'm going to my summary, where for this paper where we constrained the galaxy-halo connection from redshift 0 to 10, we showed how is the growth of this of the stellar mass. We infer how is the growth of the stellar mass of the galaxies for different progenitors. We project the mass transition in order to understand what could be the reasons for quenching. So we are here showing the star formation history for the progenitors of these galaxies, and show that there might be a correlation with something internal to the galaxy, particularly for the 1 kiloparsec, that is something that is perhaps quenching the galaxy. And finally, don't forget to visit our website, where you can obtain all these tracks and all the figures that we shine in the paper in this talk. Okay, thank you.
So I have a question about change of the stellar mass halo mass relationship between field galaxies and satellite galaxies. So what about the scatter, right? For us, you showed earlier this week that we expect larger scatter of the halo mass stellar mass relationship for satellite galaxies. So did you consider that when you were comparing?
Yeah, actually, we constrained the scatter of satellite galaxies, and we found that it's larger than the one of centrals. And also, if you saw the figure that I showed where there was the difference between satellites and centrals, when you use abundance matching, you don't take into account that. But actually, it's another source of a scatter for the global correlation, where you don't distinguish between centrals and satellites. And this will reflects that the scatter at low mass halos will increase.
So I think this might be really interesting, because when you show the evolution of the stellar mass halo mass relationship, the halo mass which shows the most evolution is that halo mass which is likely to transition from being mostly central to mostly satellite over the last.
Yeah, it's more or less the scale.
So I'm wondering, that sort of change from being mostly field to mostly satellite, is that what's going on with that evolution?
Yeah, it's a bit more complicated, because again, if there is a segregation between colors, for example, between the star forming and quench galaxies, so well, this is for centrals, but you can imagine that, for example, there are some galaxies that once they become satellites, they are already quenched, and they are already in another part of the stellar to halo mass relation, which is very close also to the regime of the quenching transition. So I think it's a bit more complicated, but I would guess that is more what you were supposing.
Let's thank Aldo again.